Hi everyone, myself Bidyutlata Sahoo, Assistant Professor in the Department of CSC, Artificial Intelligence and Machine Learning at Institute of Aeronautical Engineering, Hyderabad. This is my ninth video lecture on the course Applied Artificial Intelligence. Today I am going to discuss about the knowledge engineering in first order logic. Already I have discussed the concept, how the knowledge engineering works, what are the process. Again I will introduce and one of the classical example today I am going to discuss. These are the topic to be discussed. What are the steps of knowledge engineering process? One of the example is the domain of electronic circuits and what are the benefits of knowledge engineering process. This is the topic learning outcome for this particular topic. So after the completion of the topic, students can apply the knowledge engineering techniques in first order logic to represent the facts, rules, and the relationships, enabling the development of intelligent systems for complex problem solving. These are the steps of knowledge engineering process. In my 8th video lecture, already I have discussed in briefly. Let me introduce once again what are the steps involved in knowledge engineering process. Total 7 steps are there. Step 1, identification of the task, which is called as the goal formulation. Step 2, assemble the relevant knowledge. Based upon the goal formulation in the step 1, the relevant knowledge will be acquired in step 2. Step 3, decide on a vocabulary of predicates, functions, and constraints. Like after the acquiring of all the knowledge in the step 2, we have to give or we have to assign all the names so that there should not be any name conflict. So different predicates we will use, or for every object, like we will define with predicates, functions, and constraints. Then in step 4, encode the general knowledge about the domain. Here the knowledge representation will be done using first order logic about that particular area, that is called as encoding. And fifth step, encode a description of the specific problem instance. That means here complete description will be done about the particular domain, whatever the problem we are trying to solve. So using the first order logic, that is the fifth step. And sixth step, post the queries to the inference procedure and get answers. So whatever the description we used to do at the fifth step, now the query can be fired to the knowledge base to infer some result. So that is done in the sixth step. That will be done in the sixth step and seventh step. And during the execution of queries, during the in the sixth step, if any error comes, that can be rectified in the seventh step. That is why it is called as debug the knowledge base. So these are the 7 steps we have to follow whenever the knowledge engineering technique works to represent in first order logic. So here I'll discuss one of the classical example, the domain of electronic circuit. Knowledge engineering process, it is an knowledge engineering process in electronic circuit domain. I think we already know what is electronic, the basic idea related to electronic circuit. So this approach is mainly suitable for creating special purpose knowledge base. Now here following are some steps of the knowledge engineering process. Now I will discuss. Using these steps, we will develop a knowledge base which will allow us to reason about the digital circuit. Here the digital circuit is 1-bit full adder. So 1-bit full adder, I hope you might have known what is a full adder. I will show you. This is the pictorial representation of 1-bit full adder, which can add 3 bits to binary bit, 2 bits to binary bits and 1 carry bit, and it will generate one sum, another one is carry. So that is why it is showing 3 inputs are there, 1, 2, 3, and 2 outputs, S1 and S2. And here for the representation of 1-bit full adder, it is required 2 XOR gates are required, 2 AND gates are required, and 1 OR gate is required. So X1, X2 are the XOR gate, A1, A2 are the AND gate, O1 is the OR gate, and the name of the whole circuit is C1. So this is what the representation is for 1-bit full adder, but we have to represent the this complete full adder circuit and how it works till seventh step using first order logic. So as per the process as I have discussed, so first is identification of the task, which is called as the goal formulation. So here goal identification of the task means the circuit will be observed at the highest level and what is the goal of this circuit. So there are so many reasoning tasks associated with the digital circuit. At the highest level, we will examine the functionality of the circuit. Functionality of the circuit means does the circuit is actually add properly or not. Mean that the meaning is circuit verification. All the connections are properly done or not. Overall structure of the circuit will be examined at the highest level, and the inputs and outputs of certain gates. We should have the knowledge of all the inputs and outputs, how many inputs every gate takes and how many output every gate gives, that we should know, and whether all the inputs and outputs are connected or not. So that is what at the second level we will examine the circuit structure. So, and for example, what are all the gates connected to the first input terminal? Does the circuit contain any feedback loop? Feedback loop means like any of the output from any output from any gate, is it connected as an input to the other gate? So that is called as the feedback loop. So overall I can say the identification of the task which is done at the first step, here the overall structure and the functionality of the circuit will be checked. Here the domain is circuit, electronic circuit, that to 1 bit full adder. So based upon the circuit, all the knowledge will be stored using first order logic. So in the first step, we will examine the functionality of the circuit as well as the circuit structure. Second step is assemble the relevant knowledge, which is called as knowledge acquisition. After defining all the structure and the circuit verification, all the connections are properly there, then we will acquire the knowledge of each and every component what is present in that circuit. So in the second step, we will assemble the relevant knowledge which is required for digital circuits. So for the digital circuit, we have the following required knowledge. Everybody should have the knowledge. Those who want to represent the knowledge using first order logic, especially the knowledge engineers. So first one is the logic circuits are made up of wires or gates. So what type of wires and how many gates are used and what are the gates actually? It is used for the representation of or for the building of 1 bit full adder. So that we need to, that information we have to acquire. The signal flows through the wires to the input terminals of the gate, and each gate produces the corresponding output which flows further. That means how many inputs are coming to each gate and how many outputs are coming from output gate. For example, we'll take the example of the XOR gate. XOR always takes 2 inputs and it provides 1 output. So all the informations we should have prior to the implementation or prior to the representation. And third is in this logic circuit there are 4 types of gates we have used: and, or, XOR, and not. Anyways, not gate is not there in our circuit. Let me show you once again. Here not gate we do not have, but it is a basic gate we can say. So these are the basic gates we used to use in for any logic circuit. So one is AND gate, OR gate, XOR gate, and NOT gate. And all these we should have the knowledge. We will acquire the knowledge how all these gates work. Like AND gate and OR gate, XOR gate, they takes 2 inputs and provide 1 output, whereas the NOT gate takes 1 input and provides only 1 output. What are the truth table for all the table? How many inputs they take, how many output they provides, how they are connected, what type of wires are used. So all these kind of internal information about the structure we have to gather in the second step. So that is why it is called, this step is called as assembling the relevant knowledge. Third step is decide on a vocabulary. Now after deciding, after recognizing like all the information about the gates, wires, the structure, and the circuit verification, now we have to give the name. Because if you are an electronic so student, or if you have studied the concept of DLD, or if you have the knowledge of the circuit, then it is fine for you. But being a layman, any layman, if anybody asks what is the symbol, he or she doesn't know, so we have to explain everything. So that is why we have to give all the naming convention to all the objects. So here total 6 objects are there. One is this 2 XOR gate, 2 AND gate, and 1 OR gate, and the whole circuit which is considered as the circuit C1. 3 inputs, 1, 2, 3, and 2 outputs, that is nothing but your S1 and S2. So here in this vocabulary, as I said, here we have to give the naming convention. So here we have to choose the functions, predicates, and constants to represent the circuits, terminals, and signals, as well as the gates. First, we need to able to distinguish between the gates from each other and from each object. Now you can see each gate is represented as an object name, which is called as a constant. As I said, everything is considered as an object in this circuit. So we will use one constant name. Let the name be gate or gate x1. So GATE, that is the name of the constants, and that constant is meant for gate. So gate x1. So that similarly I can write gate x2, gate A1, gate A2, gate O1. So like this we can write. So all these gate is nothing but a constant which is meant for a particular gate. Now we have given the name of the constant as gate, but what is the purpose, what is the behavior of the gate? Now we need to understand. Well, gate x1 means what type of gate it is? It is an XOR gate. So that is why we have to use one of the function that is called as type of x1, which is equal to XOR. Similarly, we can write type of x2 is equal to XOR, type of A1 is equal to AND, type of A2 that is equal to and, type of O1 that is OR. So like this we can define all this like all these gates and their behavior using type function. And one more here predicate we will use for circuit, because the whole circuit sometimes like during the representation of the knowledge we need, that is why we are using the name of the predicate as circuit. So what is the name of the circuit here? C1. So circuit C1, only one circuit we have, that is why circuit C1. I hope you might have understood here. So gate is the name of the object, gate x1, gate x2, gate A1, gate A2, gate O1. But to recognize their behavior, we are using the function name, that is type. Type of x1 is XOR, type of x2 is XOR, type of A1 is AND, type of A2 is and type of O1 is OR. Similarly, few more things are there. Now we have to consider the terminal X. So here terminal X means the terminal T. Terminal means either the terminal will provide the value 0, input terminal, or output terminal. So in this we will consider which are identified by the predicate terminal. So how we can recognize? Here the name of the predicate is terminal X. A gate or circuit can have one or more input terminals and one or more output terminals. So here, as you can see in this diagram, there are 3 input terminals and there are 2 output terminals which are coming from, one is from X2 it is coming, and another one is coming from O1. So that is why we have used this predicate terminal X. Now how many inputs, how we can write? Suppose one input is going, this one input is going to X1. This input, the input from X1 is going to X2. Input 1 is going to X1. Input 2 is going to X2. Now how we can write? So using the function in. So in within bracket 1 comma X1. What is the meaning here? First input terminal to X1. First input terminal, which one? This one. First input terminal to X1. Similarly, we can write in 2 comma X1 means second input terminal to X1. So this is the way we can use to define the function in function for a particular input to a dedicated gate. So first input terminal to X1. Now another function we have used, that is arity. ARITY. Arity within bracket C comma I comma J. C stands for the circuit. Anyways, you can write C1 for our given circuit. So C is nothing but, in general we have written C is the circuit which accepts I inputs and provides J outputs. So for our diagram, what we can write? Arity, ARITY, arity C1. So three inputs and it provides two outputs. Like this we can mention, but this is a general function I have defined here. Arity C, I, J. That means the circuit C has I input and J output terminals. Now we'll check the connectivity. Some connections are there. So connectivity we can define with the help of function that is connected. So connected, which takes two terminal as the argument. So one is input terminal, another one is output terminal. So inside the connected functions we have written out function 1 comma x1 comma then in function 1 comma x2. What is the meaning here? First output terminal of x1, out out of 1 comma x1 means first output of x1 means this one. First output of x1 is connected to the first input of x2. This is the first input to x2 also. So this is the connectivity. This is the output from x1. It is coming from x1 and it is connected to x2. So that how we can define using the connected function. So these are the naming conventions. I hope you might have understood. One is the object gate we have, and how to define the behavior of the gate using type function. Sorry. Here I have defined the type function, the name of the circuit using predicate I have defined. Terminals we have defined both input and output using the predicate terminal. In function, out function, both in and out can be connected with the help of connected function. And the overall circuit we can define using arity function. Arity C, I, J. I is nothing but the number of inputs and J is nothing but the number of outputs from the circuit. Finally, one more convention is there, that is signal. So as we know from any electronic circuit, the signal can be on or off. So therefore we introduce two objects, two signal values. One is 1, another one is 0. So here signal, so using the function signal of t. So t stands for the terminal. Signal of t represents whether the signal of the terminal is 1 or 0. So why we are using all these terminologies while representing the knowledge using first order logic? We will not get any problem. Easily we can write the statement using predicate logic. So that is why at the third step we have to give all the names using functions, constants and vocabularies. Then in the fourth step, this is very important, naming convention is done. Now we will convert. Now the work of knowledge engineer is to represent the knowledge, to represent the facts or to represent the rules about the electronic circuit in first order predicate logic. So here to encode the general knowledge about the logic circuit, we need some facts or rules. So we will see few facts or few rules. I think you might have known already. So I will give all the examples with all explanations. First one is, if two terminals are connected, then they have the same signal. If two terminals are connected, then they have the same signal. So how we can represent using predicate logic? Let me tell you. In predicate logic, we have two quantifiers. One is for all, another one is there exist. These two quantifiers are very important. This for all stands for every and for all. This there exist for each, for at least one. So in this case we can use this there exist at least for one, right? So based upon the statement we have to use those two symbols. So in the first statement, if two terminals are connected, then they have the same signal. So here two terminals we have used in the statement. So let us define two terminals as T1 and T2. So for all T1, T2, terminal T1 and terminal T2, and both the terminals are connected, T1 connected with T2, that implies signal at T1 is equal to signal at T2. So I hope you can understand now. Terminal is one of the function we have defined, connected also one of the function, and signal also one of the function. Already we have defined in the fourth step, just we are using based upon the problem statement. And here in the problem, if then is given. Whenever, one more thing you remember, while defining any statement in first order predicate logic, if you are using for all symbol, definitely in the middle we have to use the implication symbol. That is why here, as I have used for all, here implication symbol. So for all T1 comma T2, terminal T1 and terminal T2 and T1 connected with T2, that implies signal of T1 is equal to signal of T2. The second example is The signal at every terminal is either 1 or 0. So signal at every terminal. So every term is given. So for all, let t be the terminal. So we are defining the variable t. So terminal of t, that means, that implies signal of t can be 1 or signal of t equal to 0. Either this value is equal to 1 or this value is 0. So we are using, this is or symbol, this is and symbol. You should be acquainted before understanding this one. Third one, connected is commutative. So connected is commutative means what? If two terminals are connected, T1, T2 connected, that means T2, T1 connected. How we can represent using predicate logic? So all the connected is commutative. That indicates for all two terminals connection. So that is why we are using for all T1, T2, T1 connected with T2 if and only if T2 connected with T1. So this double implication we have to use because commutative. Reverse way also it is possible. So T1 connected with T2 if and only if T2 is also connected with T1. That is the representation in predicate logic. Next example, there are 4 types of gates. Already we have discussed there are 4 types of gates normally we used to use in our for the designing of the digital circuit or any circuit diagram. So here gates, we have to define one variable for all g, gate of g, and what is gate g? As I told, gate is a constant. What is how to define the property or the behavior of the gate? Using type function. So let type of g is equal to k, you assign. So every time we will not write type of g, we will assign k. So for all g, gate g and type of g is equal to k, that implies k is equal to and, or k is equal to or k is equal to XOR, or k is equal to NOT. So k can be any gate. So if you define, so there are 4 types of gates. So suppose any specific gate is given, then we have to define based upon the input and output. So next one, an OR gate's output is 1 if and only if any of its input is 1. So how we can write any of the input is 1 means any. That means there exists. Suppose there exists a signal. The signal from the gate can be 1. That is, this is the output part. Now an OR gate's output is 1 if and only if. If and only if means this double by implication. Any of its input is 1. So how to define the OR gate? Let us suppose we declare the variable g for all g, gate of g and type of g that is equal to OR. That implies the output signal. First output signal from g is equal to 1 if and only if there exists a signal, input signal is 1. Okay. So if any one of the input signal is 1, definitely the output signal is 1. So that is why that implies output from the gate is equal to 1 if and only if any of the input signal is 1. So any of the input, that is why we are using there exists n. N is any signal, right? Next one, an XOR gate's output is 1 if and only if its inputs are different. That means for XOR gate, if it is 1-0 combination, then we will get 1. If it is 0-1 combination, we will get 1. But for 1-1 condition and 0-0 condition, we will get 0. So these two are, for these two we have to define, we have to represent using the predicate logic. So how we can define? For all g, g stands for gate and type of g is equal to XOR. That implies the output of signal from g is equal to 1 if and only if both the signals are different. Here both the signals are different. One is 1001. So how we can, one is 10, another one is 01. So that is why, so signal of input signal of first input signal of g is not is equal to the second input signal of g. I hope you might have understood. As I told in XOR gate, if both the inputs are different, then only we'll get 1. Okay. If 1-0 and 0-1 combination, the output will be 1. So how we can write? The first input of the gate and second input gate are not equal. That is why here it is written the first input signal from g is not is equal to second input signal from g. Then only it represents the XOR gate. Few more example. A NOT gate output is different from its input. That means in NOT gate, if we give 1, it gives 0. If we give 0, it gives 1. That means both input and output are different. So how we can represent in predicate logic? For all G, gate G and type of G is equal to not, that implies first output signal from the gate is not is equal to input signal from G. So why, you might be thinking why it is written 1, because there is only one output and there is only one input. So output signal from the gate is not is equal to the input signal from the gate. This is the way we can represent the NOT gate. Then the next one, the gates except for NOT gate have two inputs and one output. This is very common, and whether it is AND gate or OR gate or XOR gate, every gate takes two input and provides one output except the NOT gate. So let us define for first for the NOT gate, then we will define for other gates. So the first statement is meant for NOT gate. For all G, gate of G and type of G is equal to NOT, that implies arity function which defines the overall circuit for the NOT gate. So G comma 1 comma 1. So G is the name of the circuit which receives only one input and provides one output. Okay, which receives one input and provides which receives one input which receives only one input and provides one output. Okay, so if we provide 1, then it will be 0. If we provide 0, it will be 1. That is your NOT gate. Then similarly for AND gate, OR gate and XOR gate, how we can represent AND gate, XOR gate and NOT gate? So already we know what is AND gate. AND gate, it takes two inputs and provides one output. If it is 0 0, then it gives 0. If it is 0 0 0, if it is 0 1, this is 0. If it is 1 0, this is 0, and if it is 1 1, it is 1. So if both the inputs are 1, then only it gives 1. So for every we are not talking about how we are talking about how to represent the AND gate. We are not talking about the input and output. So in general, we can write for all G, gate of G and type of G, that is equal to K, and K is equal to 1, and that means type of G, instead of writing type of G every time, we can write assign K. K is equal to AND, or K is equal to OR, K is equal to XOR. That implies for any gate you consider, whether it is AND, whether it is OR, whether it is XOR, for every circuit, arity function would be arity function will take two inputs and one output. So that is why that implies arity within bracket G comma 2 comma 1. G is the gate which takes two input and one output. So this is the way we can represent all the formulas, all the axioms, all the rules which we need while designing the digital circuit, especially for our example for 1-bit full adder. Now, few more things. Gates, terminals and signals, gate types and nothing are all distinct. That means everything is different from each other. How to define? So, let for all G, comma T, G stands for gate, T stands for terminal. So, gate of G and terminal of T, that implies G is not is equal to T. That means gate is not is equal to terminal, is not is equal to the signal also. 1 not is equal to 0 is not is equal to any of the gate also. Not is equal to OR, not is equal to AND, not is equal to XOR, and not is equal to not, even not is equal to nothing. So everything, whether it is gate, terminal or the signal or the gates or nothing, everything is distinct. All are different from each other. This is the way of representation. Now, next one, the gates are circuits. That means all the gates are circuits. So we'll take one variable for all G. Gate of G is a gate, that implies G is a circuit. If G is a gate, how we can read this statement? If G is a gate, then G is a circuit. So gates are circuits. All gates are circuits. That is why for all symbol. So this is the way of representation of all the facts and rules. I hope you might have understood. Now come to the fifth step. Fifth step says that encode the specific problem instance, where we will describe the description about our problem. Our problem is it is a full adder circuit. Now we have to describe. We have mentioned all the rules and all here in the fourth step. Now using all the fourth step statements, we have to describe about our story. What is the goal here? How to represent for the 1-bit full adder. So here circuit C1 with the following description. First, we need to categorize the circuit and its component of gates. First statement you can see circuit C1 and arity C1 3, 2. Name of the circuit is C1. That is why we have used the predicate C1, and arity function within bracket name of the circuit, and the circuit takes these three inputs 1, 2, 3 and provides two outputs, that is 1 and 2. Okay, these three inputs and two outputs. This is the first statement. Second statement, gate x1, okay, and type of x1 is OR. We have to define, we have to describe each and all gates in this circuit. So what about this gate? So this gate is gate. We know gate is the name of the constant. So gate x1 and type of x1 is equal to XOR. Similarly, all these gates we can define. So gate x2 and type of x2 is equal to XOR. Okay, and similarly this A1, gate A1 and type of A1, that is AND gate. Gate A2 and type of A2, this is AND gate. And gate O1 and type of O1, it is OR gate. So like this we have to describe each component as well as the whole circuit. What is the whole circuit? The name of the circuit is C1, which accepts three inputs and provides two outputs. So that is why we have used arity function. Next, after defining all the connection, all the overall circuit using arity function, and after defining all these components, means the gates, the type of gates, now we will see the connectivity, how the connections have been done. So there are 6 statements are given using normal statements. I hope you can understand, it's very easy. So we already know connected is one of the function, and connected function requires two arguments. So one is in argument, another one is output argument. So or else in or out or in or out, anything is okay, but it should satisfy our circuit. So based on by following the circuit, by observing the circuit, we have to define the statements. Now the first statement you see here, connected within bracket out, 1, x1, in, 1, x2. That means the first output from x1 and the first input to x2 are connected. Okay, the first output of x1, what is the first output of x1? This portion, and this is the first input to the x2. This is x1 and this 2, both are connected. Second one, first input of c1 and first input of x1 are connected. First input of c1 and first input of x1, which one is the first? This is the first input to c1. The overall circuit, if you see c1, so for this whole circuit, first input is this one. Okay, so for the overall circuit, this is the first input. So first input to the overall circuit, that is connected as the first input to the x1, because this is x1, this is x2. Okay, now this is connected. Second one, first output of x1 and second input of a2. What is the first output of x1? This is the first output of x1. Let me erase so that you can understand. Second statement. For the second statement, it is given that first output of x1, this is the first output of x1. Second input to a2, where is a2? This is our a2, this is our x1. So second input means from here one connection is given here. So this is the second input to a2, both are connected. So with this joint, it is connected. Similarly, first input of c1 and first input of a1, both are connected. Which one is the first input? Let me erase once again so that you can understand. This is the first input of c1, okay, the overall c1, and first input to a1. First input, this c1, it is connected as to a1. This is your a1. So both are connected, right? So this is the way the connections are given, all this. The third one, first output of a2. First output of a2 means this is our a1, this is our a2. So first output of a2, this is first output of a2, and first input of o1. What is this? Is the first input of o1. This is our o1. It is connected. Okay, so this is the first output, and this is first input to o1, which is called as the feedback loop. Already I have introduced what is the meaning of feedback loop. If one of the output from any gate is connected as the input for any other gate, that is called as the feedback loop. So we have to define in the predicate logic or first order logic. So that is what it is given. Now next one, it is given as second input of C1. Which one is second input? This is the second input of C1 and second input of X1. The second input, it is the overall input to the circuit C1, and it is also the second input to X1 also. Okay, so that is what it is given in the third statement. Then in the fourth statement, it is given that first output of A1. First output of A1, this is A1, so this is the first output of A1, and second input of O1, this is the second input to O1. So this connection, it is connected. From this is the first input, first output of A1, and this is the first input to the second input, second input to the O1. Both are connected. So we have to define using connected function. Next one, second input to the C1. This is the second input to the C1 and second input to the A1. What is the second input to the A1? This one. So this connection, it is done from here to here connection. So second input to the whole circuit C1 and second input to the A1, both are connected, right? Now, first output of X2. What is the first output of X2? This is the first output of X2. Okay, and this is the first output of C1. This is the first output of C1 because there are two outputs. One is 1, another one is 2. This is the first output of X2, which is nothing but your first output of C1, which are connected. So that is why this statement is given. Similarly, third input of C1. This is the third input of C1 and second input to the X2. This is connected as the second input of X2. For third input of C1, the overall circuit, and this is connected as the second input to the X2. Okay, both are connected. Then the last one, it is given as the last statement you see here. A first output of O1. What is O1 here? This is the first output. This is nothing. The only one output is there. First output of O1 is nothing but the second output of a C1. C1 is the whole circuit. Both are connected. Same thing. Third input of C1. This is the third input of C1 and first input of A2. Where is A2? This is the first input. This is the first input. Third input of C1. So third input is the C1 and it is connected as first input to the A2. This is A2. So this A2. So this is the first input to the A2. Both are connected. So like this, all these connections we have to define. Wherever we find the wires, the connections, the feedback flow, we have to define using connected function. So this is about the encoding of specific problem description. Then in the sixth step, we'll fire the queries to check whether the system is working or not. How the system or the knowledge based system will work properly if the knowledge is represented in a correct way. If the knowledge representation is wrong or it is with error, definitely it will provide some debug, or it will provide some errors to the user. So that is why the sixth step is pose the queries to the inference procedure. So in this step, we will find all the possible sets of values of all the terminals for the adder circuit. Now this is one of the query will represent what combination of inputs would cause the first output of C1, which is nothing but the sum of bits to be 0, and the second output of C1, the carry bit, to be 1. Already we know that the full adder circuit takes 3 inputs and provides 2 outputs. One of the output is the sum of bits, which should be 0, and the second output C1, which is nothing but the carry bit, should be 1. So how we can represent? So while representing using in your predicate logic, if it accept does not give any error, that means your representation or your naming conventions are proper or are correct. Otherwise, we have to again check the representation of the knowledge. So how we can represent this particular query? So for there exists I1, I2, I3. So I1, I2, I3 are nothing but the signals. So first input signal from C1, that is I1. So here in this diagram, this 1, 2, 3, we are considering this 1, 2, 3 as I1, I2 and I3. So here we can write there exists I1, I2, I3. First input signal of C1, let it be I1. This one, and and this is AND operator. Second input signal of C2 as I2, and third input signal as I3, and first output signal of C1. First output signal means this one. This one first output, this is second output. First output is 0, second output is 1. That is what it is given in our question. So first output of C1 is equal to 0 and second output of C1 is equal to 1. So during this representation, if we get any error, that means if you do not define this input signal, output signal, or signal function, or this the existential quantifier or declaration of the variable, definitely we will get the error. So to rectify the error, the seventh step is required, where the error can be rectified. That means we have to again backtrack to previous steps, from the starting from the first step to rectify the error. So this is the seventh step, is nothing but the debug the knowledge base. We can debug the knowledge base in various ways to see what kind of erroneous behavior emerges. For example, suppose we forget to assert that 1 is not equal to 0. Definitely every terminal a signal at every terminal can be either can be on or can be off. So if you do not define that distinct function, distinct statement, all the things or all the objects whatever we have considered while defining the logic circuit, all are different. Otherwise it will give in place of 0 1, in place of 1 0, means we will get all errors, because this 1 and 0 are very important in digital circuit. Already we know that. So that is why it is one of the concept, like it is given. Suppose we forget to assert that 1 is not is equal to 0. Suddenly the system will be unable to prove any outputs for the circuit except for the input cases like 000 or 110. We can pinpoint the problem by asking for the outputs for each gate. So that is why let me conclude here. Already I have discussed all the 7 steps. So developing a knowledge base in knowledge first order logic, which requires a careful process of analyzing the domain, choosing a vocabulary, and encoding the axioms required to support the desired inferences. So all these things, the representation, analyzing about the domain, choosing the vocabulary, and encoding of axioms are very, very important compared to the 6th step or 7th step. Till 5th step is very important. Then only we will get the correct result. Let me discuss about few benefits of knowledge engineering. So knowledge engineering, it helps in creating better, smarter, and more effective expert systems. That depends upon complete the knowledge, how the knowledge engineer has represented inside the knowledge base. And the models created with knowledge engineering are robust. Irrespective of any situation, they can work. So these are the references I have followed, this Peter Nervig book as well as this YouTube link. You can also follow. I hope you might have enjoyed my session regarding this knowledge engineering in first order logic. Next class, I will discuss about one of the representation of knowledge technique, that is called as ontological engineering. Till then, take care. Bye bye. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.